Thank you very much. It's a great pleasure and honor to be here and have the chance to do this lecture. I'm a bit overwhelmed with all this praise and prizes and all that. This evening, this is not going to be an extremely scientific lecture, but rather what I wanted to do is show you some images and tell the stories along these images. And all these things are somewhere between math and physics. There is some art in there, and one of the questions we can always ask is this art? Is this artistic? We can also ask, where is the math in there? Where is the physics in there? And how are these things connected? And somehow I collected this collection of images to tell the stories with, and while I collected this, I realized there's so many connections between these things, which are somewhat surprising, some things that really also don't fit together. And then you see this a second and a third time, 1 or 2 centuries later, and it still doesn't seem to fit together. So there must be something in connections in there. So the title I put up there was Sugar Cubes, Soap Bubbles, a Revolution, and a Star. And then again, when I finalized the lecture, I realized I got it the wrong way around. The order of things is really the other way around. We will do the star first, and then the revolution, and then the soap bubbles, and then the sugar cubes, and various other things in between. Actually, the more detailed description perhaps would have been a polyhedron, start, a revolution, ellipsis, another revolution, polyhedra, more ellipses, least square, soap bubbles. A Cauchy problem is even in there, and in the end, of course, we will arrive at the soap bubbles and the sugar cubes and so on. It was promised that I would explain my latest research, perhaps in such a way that everybody here and now can understand it and take it home. We will see how far we get with that. That's not the primary ambition with this presentation. So that's the plan. Here's the first star. I'll say a bit more about this one as well. And here's the plan of the presentation. On the left side, you already see there's quite some mix of mathematicians and artists around. There will be a star, a revolution, polyhedra, soap bubbles, sugar cubes. So that's all these things. So altogether, this is 6 little stories. And then as an addition, I want to just do 1 or 2 extra remarks about images that we have for math as a whole and about the physics that's in there. I hope that you can see what's on the screen. If not, there's a few more places also here in the front rows. I always explain my students in class that my grading scheme is quite simple. There's an A for everyone in the first row, and an A- in the second row, and B+ and so on. So just to encourage them to move forward. So you're also encouraged. Okay. Story number 1 starts with this image. So I didn't bring the book because I have a reprint of this book where this is from. I hope you can see it. It's actually very bright here. It's a drawing of a polyhedron, actually a hand drawing with watercolors and all that. And this definitely is math, as you can see, because polyhedra are mathematics. It is also art, because it's by Leonardo. And the first question one could ask, I mean, we were at the Eremitage briefly this afternoon and saw the 2 Leonardos they display there. This is not one of them, it's 2 Madonnas instead. How did Leonardo get to draw polyhedra? I think that's an interesting question. And the story is, of course, connected to the guy who wrote the math book that this was supposed to illustrate. And this is this person. Luca Pacioli, who in the this is on the turn from the 15th to the 16th century, so he lived from 1445 to roughly 1514. We don't know exactly when he died, actually. He was a Franciscan monk. He was also a mathematics professor, basically at all Italian universities at the time. He moved around quite a lot. And for a certain time in his life in Milano, he actually also lived together in some shared apartment type version that we don't quite understand with Leonardo da Vinci, who at the time, Leonardo was 7 years younger. Leonardo was getting mathematics lessons from Pacioli, so Leonardo thought that mathematics was important. He also needed that for some of his engineering projects and of course also for his paintings and stuff. But actually, although Leonardo of course is a genius and perhaps the greatest genius of the Renaissance, his mathematical education was very weak. So it has to do with his family upbringing and whatever. So actually, at the time, he was over 40 already, where he was getting mathematics lessons from Luca Pacioli, who was a famous also mathematician at the time. He had published a first math book called Summa, which had appeared in 1494, which summarized all the math that was known at the time. And actually, I don't know who of you knows Luca Pacioli. The economists really know him, because Luca Pacioli wrote up the first treatise of what was known as the Venetian method at the time, which is the scheme of double bookkeeping that's still practiced by everybody in modern times. So that's why the economists know Luca Pacioli. So this is the most famous portrait of him. So clothed as a monk, but actually with all the insignia that the mathematician needs at the time. There's a dodecahedron here. There's a book here, which is probably his own. There is a compass. There is a chalkboard, which says Euclides here. So Euclid with a geometric drawing. Then there's a person in the back where there's some speculations about who this young man is. One of the theories was actually that this was Dürer visiting from Germany at the time. This is rather improbable because Dürer visited a few years after this, this painting was made. And then actually there is this polyhedron here, which is perhaps more interesting than the dodecahedron here, which is known since Greek times. This is a glass polyhedron filled with water, and it stirred quite some controversy. Let's look at this a bit more in detail. So that's an enhanced photo of this polyhedron. First, there's the physics in here, right? It's a glass polyhedron filled with water hanging from a very thin string, so you should actually be quite worried because it doesn't look very stable. And from what I read, people said that this is work of a genius. It's really amazing, all these reflections and all that. And I've also read that this is actually really bad because all the reflections are quite wrong. It's actually rather difficult to recreate what's really happening in this thing. You can see basically their reflections of some window in the roof, so the light comes from above. You can see also, we see the surface of the water from the top. That's somehow wrong, because if you look at the full painting, then we should actually see this from below, so it doesn't quite work out. But actually, if we try and recreate this on the computer, then it does look quite a bit different. So this is geometrically correct, and the reflections were tried to do with Povray. It's hard to see the surface. So there's math in there. There's also physics in there. it was also argued that surely Leonardo must have drawn this polyhedron, but again, that's not really plausible. The whole painting is not by Leonardo as far as we know. So that's this polyhedron. But let's try and understand what this polyhedron is. It's actually a quite interesting one. It's a so-called Archimedean solid, which some of these were described by Archimedes in Greek times. They have faces that are regular polygons. In this case, this is squares and triangles. And all the vertices are the same. So for this one here, at every vertex, there's 3 squares and 1 triangle. So that's what this polyhedron is. And this is computer graphics. This is, again, Leonardo's drawing from Pacioli's book. My way of describing this would be you start with a cube. That's the only one I really understand. And then you shave off the edges. And then you also cut off the vertices. And so wherever there was a vertex, a triangle will remain. This is where an edge was. There was another edge. So you see the triangles. There's one here. There's one here. There's one here. There's one here. In the end, there will be 8 of these triangles because they are at the positions where they originally were the vertices of the original cube. It's my way of describing this. There's all kinds of other ways of describing this polyhedron. So it's a rather beautiful polyhedron. And now if we go back to the star, I promised you stars, then this is Leonardo's drawing of the starred polyhedron that goes with it, because now a little pyramid or spike is erected on each of these faces. Right? And at the time, apparently they did have models. These models have not survived. So Leonardo did draw these things from models. We know that because Pacioli brags in his book about these models and about Leonardo and how great he is and whatever he did. So that's also why we know that Leonardo did the drawings of the book, which eventually was published with copper engravings of these pictures in 1509. The one thing I want to point you to is that this is A, beautiful, and B, quite interesting, also because Leonardo apparently at least invented this type of representation of the polyhedra where you can really look into them. But it's also amazing because there's a big mistake in there, which Leonardo perhaps shouldn't have made since they did have models. If you look at this more carefully, I marked the pyramids which are at the positions where there's the original vertices of the cube. And so this is one of these pyramids, a pyramid over a triangle, and here's one, and here's one, and here there should be one as well. Right? But if you look closely, you'll see that Leonardo draws a 4-spiked pyramid here where it should be only 3. So modern times we would say he got the combinatorics wrong. Now, some people would argue since Leonardo was a genius, he can't have made mistakes. He made lots of mistakes with his math. Of course, he is still a genius. And if we try and draw this today, then, so this would be, again, a computer-generated model of this polyhedron. You see that it is different from what was drawn, but actually this is a pretty good representation of the polyhedron we want to get. And so Leonardo's stars are beautiful, and they tell us a lot about these geometric things, definitely much more than you will ever understand from the descriptions that Luca Pacioli gives in his text. Even if you take them translated and simplified and everything, in this case, you can learn a lot from the images. It's very hard to learn anything from the text. So much for Luca Pacioli and his math student, Leonardo da Vinci, who did the geometry drawings. End of story number 1. We've seen some stars. Well, not quite. It turns out that this polyhedron we were looking at is still very popular, at least in Germany, And there it's known as the Herrnhuter Sterne, which is sort of Christmas stars, which are made by some company in Saxony, south of Berlin, and they export them all over the world, and they are particularly popular in Japan. And if you look at what this is, you realize that this is exactly Leonardo's starred polyhedron, again with 8 of these spikes above triangles and 12 plus 6 of them, so 18 of them spikes over square faces. Actually, 1 less because traditionally the spike at the top is missing because that's where you hang it up. If you look at the logo of the company, then you realize even if Leonardo made some little mistakes in representing the geometry, this actually is a very, today we would say, an artistic expression of, or impression of what a Herrnhuter star is. The real thing actually is much more interesting and much more beautiful. So although I love this thing of looking at historic things and saying, you know, made a mistake here and this isn't quite right, it always pays off to look in present times and see what advances we've made and what big mistakes we are still making. End of this story. Let's go to the next one. So a little German history lesson, also for the Germans present, because the Great Revolution of 1522 and 1525 is actually not in the German history books, although it should be. It's a revolution because in these years 1522 to 1525, so this is just a few years later actually, 3 very important books appeared which caused a revolution in various ways. And let me tell you what the 3 books were. The first one was a book by a guy called Adam Ries, who had a calculating and computing school in Saxony at the time, and he wrote a book at the time, the Rechenbüchlein, and this is a front page of a later edition of his book. The first edition really wasn't beautiful. This actually has some real nice cover art in there. And this is the book from which the Germans learned in German how to do the calculations, how to do additions and multiplications and divisions and rule of 3 and percentages, and what you need in real life to do stuff on the market. And this book was amazingly successful for 200 years. This was reprinted and reprinted and reprinted. And that's the point where this secret thing about how to calculate really made it to the German markets. And German economy went up in the 16th century to a large extent triggered by this book and a few similar books. So in that sense, this was really revolutionary. So this is the book by Adam Ries. The second book from the same fall was the so-called September Testament. It was the first part of the translation of the Bible into German by Martin Luther, which not only later then led to some wars and all kinds of troubles and all things, but it definitely is also important for Germany. I'm not showing you this, I'm just showing you one little quote by Luther, the German religious revolutionary, if you want, which says here, so this is in ancient German, it quotes Luther as saying that medicine makes people sick, mathematics makes them sad, and theology makes them sinful. I had a very leading Berlin philosopher and historian explain to me what Luther meant by that. You can ask me later at the reception why medicine should make us sick, mathematics sad, and theology sinful. It's not our topic for today. This is a very famous quote of Luther. It turns out it's not by Luther. It was invented later, but doesn't make it less famous. The third book I want to talk about is a book by, again, an artist who probably they have quite some of his works at the Eremitage. Albrecht Dürer, leading German Renaissance artist, famous for his paintings. But actually, this is what he did is a math book called Unterweisung der Messung mit Zirkel und Richtscheit. So this is teaching how to measure with a compass and ruler. And so he's explaining geometry to the Germans, in particular to the artists and to the architects, who would need this quite a bit. And there's things in there that are quite mathematically remarkable, like there's one page where he explains sort of what sizes you have to do inscriptions on buildings if you do them in several rows, if you want that from a viewer standpoint, the lines have the same height, and which means he draws a curve there which you will easily identify if you're a mathematician as the tangent function, that sort of things. But Dürer also explains a lot of the classical Greek mathematics, including the conic sections. And this is the page where he explains how to get the ellipse by cutting a cone. And if you look at this a bit more carefully, you will see that he sort of already, you don't have to read the text because the picture tells it all, but how you sort of do this drawing in order to get the ellipse. Now, if you look at this a bit, you realize it's not a very convincing ellipse, actually. It's more like an egg. And perhaps Dürer should have known better. Always nice to see mistakes, but there's two things one could say there. One is that Dürer was very precise in distinguishing an exact construction from an approximation. And what he's showing here is a method how to get an approximate drawing of an ellipse. So actually for that, it's pretty good. Yeah?
At the time in German, the meaning of the word ellipse was ellipse or oval, or just a geometric figure or any shape.
So what he meant here, he's quoting Euclid, and this is supposed to be an ellipse as a conic section, but actually Dürer writes in German, and he introduces German terms for the objects, and the ellipse, yeah, he says ellipsis, but then a few lines later he says in German he will call this Eilinie, which is the shape of an egg, really. So he may have missed this point that a correct ellipse has two focal points which are equal, and it should have a horizontal line of symmetry. He also has names for the hyperbola and so on. I showed you the ellipse because of this little slip, but also because we'll need the ellipses later when we go back to the stars. Okay, so this is Dürer from this revolutionary book. The second comment, blaming Dürer for not getting it quite precise is nice, but if we look at modern times representations of conics, this one from the Handbook of Applicable Mathematics, 1985, very expensive volume published by, I think, Wiley at the time, and if you see how wrong this drawing is, and it's not only not precise, but it's so badly wrong, this would have been a slightly corrected version I could offer to them. Then you see it's not really progress from 1525 to 1985, but actually it's quite a bit of regress. So we have to be careful. I mean, if you want to find this in the library at some point, this Handbook of Applicable Mathematics in several volumes published in the mid-80s has so amazingly bad images in there, a lot of them. This is just one example that it's really fun to look at that. It also got all the polyhedra wrong and badly wrong. So there's lots of examples in there. Okay. We do a step, basically sort of fast forward one by 1 century. So Leonardo was just before 1500, Dürer was 1525. Johannes Kepler, a German math teacher, basically for most of his career, badly paid, earned his money more as an astrologist than from anything else. But he made some very important discoveries, as you well know. This is Johannes Kepler. He was always very meager and very slim all his life. This is a later portrait. And what I want to show you is some of the Kepler concepts and discoveries sort of in the order of publication, because that's somewhat interesting. So that's why I put a year here. This is 1596. Kepler's first book, Mysterium Cosmographicum, which contained this suggestion that the planets, the 5 of them, or the 6 of them, known at the time, could be explained by having their paths sort of along the shells which are defined by the regular Platonic solids. So you put a sphere and you put a cube inside, and then you put a tetrahedron inside, and then a dodecahedron, and then an icosahedron. And this is a drawing from Kepler's book. Very interesting suggestion, which somehow connects the polyhedra and their sizes with the sizes of or the diameters of the paths of the planets. As we know today, it doesn't quite work out already because the number of the planets isn't right. But it was an interesting suggestion. Actually, it's pretty accurate. It works out quite well. And he did later studies on this. I'll show you a few slides down. And this was not easily discarded, although it was discarded in the end. However, what they also already Kepler discovered is that there's sort of a gap basically in there between, I forgot which planets this is, which is where the planetoids are. Okay. So this is 1596. Then 1609, a few years later, Kepler discovers and makes the suggestion that the planets are really not on circles, as Copernicus thought, but indeed on ellipses. And he published the first 2 of his laws of planetary motion. The third one was quite a bit later. This, of course, is not original Kepler, but this is 400 years later a German stamp, which shows the Kepler laws and the ellipses and all that. So that's a 2009 stamp. So this is Kepler 1609. Then Kepler 1619, 10 years later, his next book, he still elaborates and tries to salvage this theory that actually the sizes of the polyhedra would determine the distances between the planets. And so this is a schematic drawing which really shows you in which sizes you have to take the polyhedra in this. I found it interesting that he was doing this sort of studies at a time where he should have by now understood that they are on ellipses in the first place and so on. So he was reluctant in giving this up. The same book, 1609, called Harmonice Mundi, it's a very long Latin title, also contains all kinds of studies of the polyhedra. So somehow also Kepler was connecting his astronomical studies with his geometric studies in a very interesting and beautiful way. And so this is a plate that you find from that book, which contains all kinds of interesting things. It contains here the Platonic solids, together with this idea that they would be connected with the 5 states of matter, from water to fire and so on. There's construction schemes for the Platonic solids. There's sort of a net here. Then down here, this is what we would probably call zonotopes today. And this is starred polyhedra, and actually this is the first 2 of the 4 Kepler-Poisson starred polyhedra, which in a generalized sense could be viewed as regular solids. discovered by Kepler and published in this book 1619. So there is polyhedron theory in there, and actually starred polyhedra, so that makes the connection to these things that Leonardo was drawing. Actually, so this is modern images of these Kepler polyhedra, which are regular polyhedra but not convex in a certain sense. And here is another plate from Kepler's book, because what Kepler did and achieved in there is basically classify these Archimedean solids and prove that there's no more than the ones that we know. And for example, if you look at number 10 here, that's the one that we had studied in the beginning, and because that's the one that appears in the Pacioli painting and in the Leonardo drawing, so it's definitely an interesting one. We're talking here 130 years after Leonardo and Pacioli's book. So that's the polyhedra here. And we make the next step, and this is now quite some step, from 1619 to 1801 to Gauss. So this is Carl Friedrich Gauss in a portrait that was done during his lifetime. As far as I know, one copy of this is here in Petersburg. The other copy is in Berlin at the Academy. That's a photo of the drawing in Academy. Basically, everybody in Germany, at least a few years ago, knew Gauss and knew what he looks like, because he was on the 10 marks bill until the euro came. So this is Gauss. Of course, you immediately see the mistake that the portrait is the wrong way round. They flipped it over because apparently that's needed for this type of bills. And you see Gauss here with a few of his mathematical inventions. Actually, the one that is, of course, important for statistics and all that is this, what we call the Gauss curve, the bell-shaped curve that appears whenever you do statistical experiments and repeat them and so on. And I hear that this has been rather popular also in Russia a few years ago, where it showed up on demonstrations like on Bolotnaya Square, where people said, we believe in Gauss. So it's...
Why does it touch zero without the distribution? Why is it important?
In this drawing, it may be a resolution problem. I don't know. We could. It's not. I have a much better picture or a higher resolution on a laptop. We can look at it later, but it may well be. Yeah, you're very welcome. Yeah, actually, good point. I mean, I don't know. Should this be sort of really visibly above zero here? Yeah. No. Yeah. So I didn't bring the bill. This is one from my private collection, but I did bring a high-resolution scan, so we can look at this more closely then. Okay. Anyway, so why is Gauss so famous? I think today we know Gauss primarily perhaps as a number theorist, and this is his Disquisitiones Arithmeticae, which he published age 23 or so, which is a milestone in number theory. But at the time, Gauss was known for that because no one understood that book anyway. And I think he was quite disappointed about that. But he was famous for the discovery of a planetoid, so for his work in astronomy. And this is a handwritten page by Gauss, which chronicles his computations for the planetoids. And there's this little corner here, which I also have larger for you, where he says Ceres found again by Zach in December 7, 1801. So Gauss was proud of this discovery. Down here you see on a different planetoid, this says the von Zach's first observation of Pallas on 4th of April, and so on. So this is the lines of the planetoids. This is what made Gauss famous at the time. They had discovered this Ceres, then they lost him after 2 weeks, and they didn't know where to find him again, and then Gauss told them. Now the way Gauss tells the story much later, and it turns out this drawing also is done a few years later, he did computations using the method of least squares, which he either discovered or at least refined for this purpose. And this computation made it possible for him to compute where they should look for this planetoid. Apparently, Gauss is sort of exaggerating there a bit the methods that he used at the time. I'm not sure whether this has been completely recalculated, what he calculated at the time. And if you look at this also, this is ellipsis, but it's a planar representation of this, and it's so not quite clear whether he computed in this planar representation or what exactly he did. But this is, at least in Gauss's handwriting, his record of the discoveries which were done from his computations. So that's Gauss, 1801. Again, ellipsis, no polyhedra around this time. Now I want to make a jump into recent times and current work, and jump from the planets to the soap bubbles. And again, let's start with some art. Unfortunately, the colors don't come out very nicely here, but I hope that you can see the soap bubble here that this little Cupid is having. And so this is Rembrandt. This is in Vienna in a museum. And his drawing of this little Cupid with a soap bubble. Apparently, this is on a little bowl, and he has a straw in his hand which was used to blow the soap bubble. So this is how well Rembrandt could do it. It turns out drawing, painting, doing soap bubbles is difficult. And you really have to try yourself to realize how difficult that is. And Rembrandt, of course, is a master. There's not that many of them around in art history, it seems. Here's another one. This is a drawing by Manet, quite a bit later, well, a few years after Gauss died, if you want to get the years. So this is 1867. And in this case, perhaps the realistic depiction of the soap bubble wasn't sort of what Manet was heading for anyway, but the Rembrandt clearly gets the reflections much more the way we would expect them than Manet. This is sort of the art of soap bubbles. The math of soap bubbles, as you might know, is pretty complicated. This is the whole history of geometric measure theory fighting with this. I just have the portraits of Federer and Fred Almgren here. Frank Morgan is one of the people I studied from, who's doing soap bubbles, and all of them are present as book authors also in geometric measure theory. John Sullivan, Berlin, is also a student of Almgren, and this is depicting him with soap bubbles, real soap bubbles. And this is, I would say, a piece of art, but this is Computer Graphics 1990 by John Sullivan. And let's stare at this for a while because it's actually a quite amazing thing. So it's a computer-generated image of a cluster of soap bubbles. One thing that's interesting in there is that if you look in the inside, so I don't know how far well one can see this here. So this is 4 big bubbles in the shape of a tetrahedron. And then there's these 2 smaller enclosed bubbles here in the middle. And one thing that's interesting in there is that this shape here in the middle clearly is not a part of a sphere, but actually it's saddle-shaped. Now, why is this interesting? Well, first point is this is interesting because we all know that soap bubbles are perfect spheres, if you let them be that, and this one isn't. So on the inside, there's suddenly a piece that is not a perfect sphere, but actually it's something like a saddle-shaped thing. Now, interestingly enough, this also implies that these spheres out here are not spheres. Here's the argument of, in short, the way I learned it. By symmetry, if one of these things was a sphere, then all four of them would have to be spheres. And now you look at the lines where these spheres come together, and it turns out that Plateau's rules tell us that at such a line there's 120-degree angles. And now we have Cauchy data, and that implies that if this is a perfect sphere and this is a perfect sphere, then this next surface here is also a perfect sphere, or it's flat. And now if you continue this argument to the inside here, it comes out that this thing also has to be a perfect sphere or flat. It isn't, which means also these outside things are not spheres. Now you could ask, it might be close to spheres, and as you see, it's close to spheres. So I asked John Sullivan how close it is, and he said he doesn't know. Might be interesting to explore whether it's still true that these things have to be at least close to spheres in some reasonable ways. But all of this is discoveries that you can make really visually in this case by doing these computations. This is computed by Surface Evolver, which is a program that models sort of minimal surfaces and constant curvature surfaces and things like that. And then this is using RenderMan, which by now is standard software in Hollywood, to actually generate these type of images. And this is state of the art, or beyond state of the art, in 1990. You can ask, since this is also a physics conference, how about the physics? John Sullivan got it pretty right, these reflections and all that. So he tells me he used his optics college textbooks to model these things at the time. Of course, if we go from 1990 to 2013, then we can do much more now. This is Jamie Sethian in Berkeley, and modeling sort of the physics of soap bubble clusters, including bubbles exploding and the shrinking and all that. So he has movies from this, so this is stills from a movie. So we are making progress even on this area. That's the soap bubbles. Again, if we ask about beauty, you might prefer to take the Rembrandt home instead of the Sullivan or Sethian if you get the chance. Sasha. I don't know, one would have to look at this closely. My guess would be that once we've destroyed this belief that the surfaces in bubble clusters have to be spheres, probably most of the time they aren't. Sorry? Yeah, but as we know from real life, it's unstable. So, yeah. What's modeled in here is also the water dripping and going down, and that's why they eventually break and that sort of thing. So this is beyond computer graphics. This here is really physics simulation, and that's also why it's much harder, of course. Okay. The last thing in my stories is we are looking at images which actually also motivated some of my research, and I'll here's my short version of, actually you know this from lectures by Sasha Babienko on discrete integrability. the point we start out with is the observation that if you know 7 vertices of a cube, then you also know the last vertex, right? Because these vertices determine planes, and to know where this lies, you just have to intersect the planes. So that's a rather simple observation, which gets you pretty far in a number of different directions. But in particular, this is sort of a stepping stone we can use to look at discrete Cauchy problem on a cubical grid. The cubical grids, this is the computer graphics I can do with Xfig. And that's what I call the sugar cubes, because at least in Germany we have these sugar cubes orderly in boxes. If you buy sugar in the supermarket, that's how you can get it. That's how I can visualize it, but there's much better visualizations around. Again, I'm not sure how well you can see this. I mean, this drawing even has a Rembrandt-like perhaps quality, but actually this is pencil drawing by M.C. Escher, who is an interesting artist for all kinds of geometry anyway. This is a photo showing him with a sphere and his own portrait reflected in the sphere. This is, I think, a woodcut done by him based on this, where you can study the geometry here in quite some detail. And Escher is famous for getting things pretty right, even if they are very complicated. Now, there's these famous hyperbolic tessellations by Escher that I don't want to go for today, but what inspired me is this cube drawing, where this is sketches from 1952, so some 60 years ago, I guess, which are actually quite amazing. And this is sort of his final product. And the way I view this, this is still the sugar cube partition of space, but now with sort of a direction which really goes off in some direction. And now if in a pattern like this, where the cubes come one after the other, we use this rule that 7 vertices of the cube determine the 8th, then you can go into such a structure and can say, if I know some of the vertices, then all the other vertices in a certain direction will all be determined. This means suddenly we get a structure, this tiling of cubes, where you just fix a few vertices at the beginning, and then all the others, or many of the others, will be fixed sort of by inference. This is discrete Cauchy problem in a certain sense. This is a geometric discovery, which you can really build into polyhedral structures. And here's one thing we did with that. Actually, this is 3 times the same thing. I just flipped over the graphics, as you can see from Escher's signing here, to see that this is sort of different views into a cubical 3-dimensional grid, which give you different perspectives. Now here's the problem we solved with that, and and this is now, well, I start with Legendre, not yet cutting edge research. Legendre, 1794, his geometry book contained this claim. The proof was only done in the 20th century, really. It said that for a 3-dimensional polyhedron, the space of realizations has dimension the number of edges plus 6. So for example, this says that if you take a cube, this has 12 edges, so you have 18 degrees of freedom if you want to realize a cube in space. And actually that's quite plausible, because this had 6 faces and each face has 3 degrees of freedom. So that's the dimension of the space of realizations of or redrawings, if you want, of a 3-dimensional convex polytope. The important thing here is that if you get a larger polytope with more vertices and edges, then the space will get larger and larger. So 3-dimensional polytopes get very flexible if they get large, and they have lots of degrees of freedom. And degrees of freedom is a topic that's basically hidden in a lot of what I've said up to now. For example, if you look at Gauss's ellipses and see how many points does he really need to know where the ellipse is, that's also a degrees of freedom count. That's quite interesting. Now, this is Legendre's observation, and then for people like me who study higher dimensional polyhedra, they ask then, is it for high dimensional polyhedra, is it also true that if they get complicated with many faces, then the realization space gets larger and larger? We know from work by, among others, Kolyamnev, that these realization spaces of high dimensional polytopes get more and more complicated. So actually they are quite a mess. He has more precise versions of saying that, but they are quite a mess. But it turns out that there's examples of polyhedra which get larger and larger and larger, but the degrees of freedom don't. And here's theorem, joint work with my student Karim Adiprazito, which says that there's arbitrarily large in number of vertices four-dimensional polyhedra whose space of realizations does not get arbitrarily large. It's dimension smaller than 100. If you don't like that, here's a different version of the same thing in still higher dimensions. In dimension 69, we can construct polytopes that are basically rigid. So they have only one realization, except you can, of course, transform space. That's sort of the theorem we can do. What we would like to do is to combine these two things and say in dimension 4, there's infinitely many that are projectively unique, which would give us a dimension here, which would be 4 times 6 is 24. So with the 100, we are quite a bit off still, but that's optimizing. So that's recent work. I just want to show you the idea that's behind it. And the idea is exactly, we look at this sugar cube tiling. Now this here is sort of a schematic sketch from our paper, which says we have a three-dimensional polyhedron, and if the faces are quadrilaterals, then we can build them up one after the other. And so these two faces are already fixed. And then comes the next face. But if you do this with three-dimensional polyhedra and quadrilaterals, then of course here's a new vertex. And this new vertex, again, you have 2 degrees of freedom, even if the plane is determined. If you do exactly the same thing 1 dimension higher, and instead of the quadrilaterals, you use little cubes, and you work your way in your cube tiling, sort of the way Escher does it, sort of diagonally into space, then suddenly you get this rigidity in the problem that you need. Here's another representation, also again from the paper, which says we do 4-dimensional polytopes, but here's the 3-dimensional thing. And if you can do such a thing as doing a ring of 3-dimensional cubes around a 4-dimensional polytope, which actually won't be a ring but a torus, then you can have the structure that one ring determines all the next rings, which means there's only very few things you have to fix, and then everything else will be fixed from there. That's as much as I wanted to say there. The paper is going to come out in Invenciones in a few days, apparently. They're just typesetting it in the moment. So it will be a 40-page Invenciones paper, which I can't put into 4 minutes here now. So I'm not even trying. But that was the idea, and I can tell you it was Escher that inspired that work, plus knowing some things about discrete Cauchy problems that I learned in our discretization project. That's it for these stories. I want to round it off with just a few images, sort of a special hobby of mine, looking at not now particular images, but I want to see an image of mathematics as a whole. And my impression is that even in high school, or even students at the university, they learn various things in mathematics, but they learn very little about what is mathematics as a whole subject. Now I can tell you how I learned what math is as a whole subject already as a schoolboy. I had a book, and this is a series that's very popular in Germany. These Was ist was books, originally they come from the US, but when they had died out in the US, they were still done in Germany. And so this I found a few years ago on a bookshelf in Berlin. I found out that this math volume still exists. And so this cover of this book is trying to represent what math is about. And then you buy this book, and a lot of the topics that are on the cover will reoccur in the book. And now if you look at this a bit, then you see there's interesting representation of various things that are supposed to make up mathematics as a whole. One is there's lots of physics on there. I mean, here's a vibrating string, and up there there's some spaceship. Then there is a fractal, of course, because sort of an iconic image from mathematics. This is not lottery, as you could guess, because the numbers are too high. It's prime numbers. There's polyhedra there, the icosahedron. There's some chance also, because there's a dice. So that's what math is represented by. Now, I saw this book on the shelf and bought it because I liked this, but I had remembered it differently from when I was a school kid. So when I went home to Munich, I asked my mother whether these volumes are still around, and she said yes, just told me which shelf to take it from. And this is the book I had as a boy. And this gives you a completely different picture of what math is about. In particular, I think it portrays math as a historical subject and hardly anything else. Right? So this is 1963. Actually, it's the cover of the original US edition, basically, which is from 1961. This here is from 2001. And then looking at it a bit deeper, I found out that there's more volumes around. This is still different covers for partially the same book. This is 1983. And I think this was first published even in the 70s. You find that set theory and sets and intersections was considered something fundamental that every kid has to learn and be excited about. There's a spaceship, there's pyramids, and all that. There's here, we find our ellipse again, and a rather strange representation of a system here that doesn't quite work. And there's also a strange Mobius strip here, right? I mean, the whole point of the Mobius strip is that it has only one side. So to have a two-colored version is really strange. Actually, they corrected this cover. A few years later, you could buy this with a completely green Mobius strip. Anyway.
There's only one side. It's
yeah. So the current version, or the later version had it completely green. Yeah. This is the current cover. And so this is the 4 representations of what math is about just in this books for school kids. And you see this is a rather changing image of mathematics. This is the current version. Gauss is there as a younger man. There's still fractals. There's chance. I talked to the designer of this, and she said pi is there because she always liked that. And this large red pi, she wanted to have that on there, and that's right on there. So this is my not only math in one image, but also the historical development of the image, at least the way they sell it or advertise it to school kids in Germany still now over the ages. And that's also the end of my lecture. Some of these images are in my picture book, which up to now exists only in German. We'll see whether that's translated. Let me end by saying thank you for sponsoring a lot of this. This fish here is the logo of our Discretization in Geometry and Dynamics Collaborative Research Center, Berlin-Munich. Sasha Babienko is the chair, where we do a lot of these research that I only touched upon a bit. And the sponsor for all of that is Deutsche Forschungsgemeinschaft. And I want to say thank you to you for listening. Thanks for them to bringing me here. Thanks a lot.